Take a look at section 10.4, Inscribed Angles and Polygons. Let's go ahead and get started with some of our vocabulary right here. First things first, we talk about an inscribed angle. And when we think about inscribed, I want you to think of an angle that is inside. And more specifically in this section, it's an angle that's inside of a circle. So what you're going to see right here, I already have a circle drawn out. And I want to go ahead and draw. I've got a vertex that's actually on the circle, and then I've got two segments, or you can go ahead and say we've got two chords right here. So we can go ahead, we've got, based off of this drawing, that would be an inscribed angle. And one thing to make sure to add, we have right here is that the vertex is on the circle. Okay. So there we have an inscribed angle, an angle that is inside of the circle, but the vertex happens to be on the circle itself. As we take a look at the next term of intercepted arc, this right here is the arc between two raised lines or segments. So piggybacking on our diagram right here, in between the angles, I'm going to go ahead and highlight in blue right here this arc. And that right there would be your intercepted arc. It is between the two between the angle. All right, easiest to put it that way. Now we'll take a look at subtend a little bit more. Actually, we'll just talk about it right now. In this diagram right here, the subtend is going to be the chord that's in between the two endpoints of the ray. So if I go ahead, you're going to see it in green. I want to draw a line right there. And that is the subtend. Okay, and the subtend right here are endpoints of a chord or arc that lie on the same side of an inscribed angle. Then the chord or arc is set to subtend the angle. When we take a look at the core concept further down, you'll see the definition written out for you. Now let's go to this next term. We have inscribed polygon. Okay, an inscribed polygon is a polygon with all vertices on the circle. Okay, and so if you look at the diagram right here, I've got a circle and I've got this square that's inside of it. Now, one of the things that I use to help me to remember the term inscribed is inside. Okay, so if you think inscribed, think right here, inside. Why? Because the polygon is inside of the circle. All right, so that would be an inscribed polygon when the polygon is inside of the circle and the vertices happen to be on the circle as well. But with this same diagram right here, I could also say and define it differently. I could say that the circle, or we have a circumscribed circle around the polygon. Okay, remember, if you think about circumference, it's the distance around the outside. So for circumscribed, think right here, outside. And circumscribed circle, outside the circle. The circle is outside of the polygon. So right here, a polygon that contains the vertices on a circle, it's almost the same. It's like the same thing as inscribed. But the difference right here is when I say the polygon has been inscribed, it is inside of the circle. When I go ahead and say circumscribed circle, that means that the circle is around the outside of the polygon. But in the end, it does describe the same thing. It's just presented differently. All right. So we go ahead and move along. An inscribed angle right here, once again we talked about that, is an angle whose vertex is on the circle and whose side contains the chord of a circle. The arc lies between the two lines, rays, or segments, and is called an intercepted arc. So right here, this leads us to the subtend part, so that if the endpoints of a quarter arc lie on the insides of the inscribed angle, then the quarter arc is set to subtend the angle. So right here, we're just go ahead and saying that, look, this angle right here, the quarter arc, it happens to subtend that angle. And so it says angle, arc AC subtends B, or we could also say that right here, segment AC subtends angle B, because it's in between that angle B right there. We got key theorems here that you're going to need to memorize, especially this one, because there's an equation that belongs to this. To find the measure of an inscribed angle theorem. So what we're trying to figure out right here is this. To find the measure of an inscribed angle is 1/2 the measure of its intercepted arc. So in the equation, what they're saying here is, let me go ahead and I'll highlight this arc AB. And so the equation says if you take half of this arc, that will equal angle ADB right there. So we have angle ADB, and that's equal to 1/2 the measure of arc AB. So this right here is definitely something you're going to want to memorize. You can see, why is this angle inscribed? Look at where point D is. It's on the circle. Okay? It's not in the middle. Now, if it's in the middle and the vertex is on the center, then it's a central angle, and you just need to figure out what that angle is. This right here, we have the actual angle on the circle itself. Let's take a look at theorem 10.11. We've got inscribed angles of a circle theorem. So I've got two angles here that happen to be congruent. But the key thing here is that they both share the same arc, right? If I take a look, we have this arc right here, arc AB. And how do I know they both share it? Well, let me go ahead and highlight and show you what angle A, we got angle ADB right here. Okay. And then we also have angle ACB. And you can see that they both have the same arc, or the subtend to the same arc AB. And so what that tells me is that those two angles right here are congruent to each other because of that. So if we have two angles right here inside of a circle or inscribed, and they both intercept the same arc, then the angles are congruent. All right, once again, we talk about inscribed polygon. Once again, if it's inscribed, it's inside. Okay, so we have a polygon that's inside of the circle, or we could also say that the circle is on the outside of this polygon right here. We move on to theorem 10.12, inscribed right triangle theorem. Okay, so how do I know right here that this happens to be a right triangle? Okay, how I know that is, one, you could see that right here I've got this segment. This segment happens to go inside or across to the center, meaning it's the diameter. Okay, so one, you have to have one of the sides be the diameter. So it says this: if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. Conversely, if one side of an inscribed triangle is the diameter of a circle, then the triangle is a right triangle. Okay, so right here, let me highlight this. Absolutely critical. Why do I know that this is a right triangle? Because one of the sides happens to be, or the hypotenuse, or one of the sides happens to be the diameter of the triangle that you see here. So if it does, you have to know that it goes through the center. If it doesn't, then we cannot say that this is a right triangle. All right. So if it is a right triangle, or if we have a right triangle inside of a circle, one, the hypotenuse goes through the center. Or if I don't know if it's a right triangle, then in the diagram, I have to be able to recognize that one of the lines or one of the segments goes through the center. Okay, so that is the key thing right here. The diameter that you have, one of the sides must be the diameter. Simple as that. Inscribed Quadrilateral Theorem, Theorem 10.13. Okay, a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So, if we look right here, opposite angles like angle E and angle G, okay, those two must add up to 180. Angle F and angle D must also equal 180. All right? And so ED or DE, F, and G lie on circle C if and only if the angle D plus F is equal to E plus G. And that all equals to 180 degrees. All right, so let's put it all together and let's see how we could solve our extra practice. Once again, not only are you going to be using the skills and the terms that you learned in this section, but almost everything that you've learned throughout, even from like algebra, even from this year, you're going to have to use that to solve these problems out. Okay, so I look right here at this diagram, and one thing that sticks out to me is that, hey, look, if I look at segment CB, or the chord, or now more specifically, that's a diameter, I know that I have myself a right triangle, right? We just mentioned right here, we've got that theorem that we talked about, the one about the inscribed right triangle. So one thing that I want to go ahead and put right here in our diagram is that the fact that this is 90 degrees. Why is that important? Because take a look. Question 1 says, what's the measure of angle A? That right there is 90 degrees. Using that inscribed right triangle theorem. Okay, so next up, we'll take a look at angle C right here. Well, I have right here 2 out of the 3 angles, right? Because a triangle itself is equal to 180. So if I take 180 and I set that equal to 90 plus 28 plus angle C. And remember, I want to always try to come up with an equation to help solve this out. You can go ahead and simplify this and say that angle C ends up equaling how much? Hopefully you end up with 62 degrees. There's a measure of angle C. Next up, we got to find B to C. Okay? Well, we've got 2 out of 3 sides. I've got a right triangle. So one way I could use or solve this is, excuse me, is using the Pythagorean Theorem. But we learned a few other things the last chapter. Remember, we learned SOHCAHTOA. So if you want to use that, you can as well. You take your pick. Now you have the option, you have the power to do that. I think right here on this one, since I know this is a right triangle, it might be easier just to go ahead and use the Pythagorean Theorem. But you could use sine, cosine, or tangent, depending on which angle you want to use. And remember, you cannot use the 90-degree angle. It's got to be one of the acute angles if you use SOHCAHTOA. All right, so we go ahead and put all that together. Simplify this for you. We've got 7.3 squared. I've got 59 or 53.29. Now, do not round, okay? I kept saying this before, but do not round right here until the very, very end, okay? And that right there is important because of the fact that if you keep rounding throughout the question, when you get to the end, you've rounded so many times that your accuracy is not going to be there. Okay, so you got to make sure when you show your work, make sure you have all your numbers down and then wait till the very end to round things out. So when I square root both sides right here, I end up with BC is equaling to 8.276. And if we go ahead and round that to the nearest, looks like I think they want you to round to the nearest tenth, this becomes 8.3. All right, and there you go. We had now found B to C, 8.3. Next up, let's take a look. We were trying to look at arc A to C. So if I look arc AC, it's up at the top in this diagram, and it subtends angle B right here. Okay, if I look at angle ABC, we're looking at 28 degrees. All right, so remember we have a theorem, we had an equation that we used right here. And it is the measure, if I take the 1/2 the measure of the arc, that right there is equal to the angle, the inscribed angle, which in this case would be angle ABC. They give us, we have to have one of the two unknowns right here, and if you look, we know what angle B is. It's 28. So if I go ahead and put 28, that's equal to 1/2 the measure of arc AC. So I got to get measure of arc AC by itself. So I'm going to multiply both sides by 2, because 2 times 1/2, that equals 1. And I have the measure of arc AC is equal to 2 times 28, which is now 56. And so there is the measure of arc AC. We've got ourselves the inscribed angle. Okay, so we got that right there. We're using another theorem, the measure of an inscribed angle theorem. And then lastly, let's take a look at the measure of arc A to B. Okay, we could do the same thing right here. Okay, because I know what angle A, or sorry, angle ACB, that's equal to 1/2 the measure of arc AB. So let me go ahead and erase a few things right here to kind of give you an idea of what I'm exactly looking at. We have the measure of arc AB, which is right over here. It subtends this arc, or subtends the angle ACB. So that's why I have right here a measure of angle ACB is equal to 1/2 the measure of AB. All right. So what does that all mean? Well, I have to know what angle C is, or measured angle ACB, and based off of number 2, we realize that that is 62 degrees. So if I take 1/2 the measure of arc AB, I've got to get AB by itself, or that arc. So same thing, we'll multiply both sides by 2. And the measure of arc AB ends up equaling 124 degrees. So this is 124. Okay. I could also found that arc by putting together all the other arcs that we just found. Now, if you recall, one thing from earlier on in the section or this chapter is that take a look at my diagram. And I want to go ahead and highlight arc BC. We should be able to figure out the measure of that arc. What is it? Well, because I know that B to C is the diameter, arc BC is actually 180 degrees. In number 4, we found right here that arc AC is 56. So that means that if we take a look at arc BAC, that whole thing is 180, right? The measure of arc BAC, that's 180. If I know half of it, or sorry, not half, but AC is 56 degrees of it, we could go ahead and subtract that, and you'll end up with 124, which is the remainder. Okay, so that's another way you could have solved this problem out as well. But that's if you have all the pieces there. I went ahead and solved it like how I did there, just because I want to make sure you guys see how the theorem ends up working more than one time and one way. All right, let's go ahead and move down to number 6. We have name 2 pairs of congruent angles. All right. Well, let's see some angles that we have here. I'll go ahead and highlight one angle. I've got angle A, angle B, and angle D. I also have right here angle D, C, and A. Now, why am I coloring in those angles? Well, I could see right here that both of those angles they've got this arc that they share. Okay, that arc AD subtends angles ABD and angles DCA. So right here, I'm going to go ahead and say that these two angles are congruent. So that would be one pair of congruent angles. And so let me go ahead and put right here angle ABD is congruent to angle DCA. And based off of those two angles as well, hey, maybe there's another one. There's supposed to be two. So what's the other one right here? Let's go ahead. Let me highlight this arc right here, B to C this time. Let me go ahead and erase what I have right there. And if I take a look and go ahead, let me highlight now angle BAC. You can see it intercepts arc BC. And then we have right here angle CDB. It also intersects arc B to C. So that tells me that these angles right here are also congruent. So I've got angle BAC is congruent to angle CDB. And those are your two pairs of congruent angles right here. All right. And that right there, we have our inscribed angles of a circle theorem, 10.11. Lastly, take a look at number 7. I've got this polygon that is an inscribed polygon. So in our last theorem, we have the inscribed quadrilateral theorem. It says that if we have an inscribed circle, or quadrilateral is inscribed, then the opposite angles are supplementary, or they equal 180. Okay, so knowing that right here, these are my opposite angles. M plus 65 equals to 180. So we can go ahead and subtract 65 to both sides. And M is equal to, right here, 115. And then we take a look at the other set of opposite angles, angles D and angle N. Or sorry, angle D and angle B. And so we have N, which is angle B, plus 100 is equal to 180. So after subtracting 100 to both sides, N is equal to 80. And we have now found the variable of each. All right, so there you go, section 10.4. If you appreciate what I did for you guys, make sure you subscribe, please like, hey, even add a comment, and I'll get back to you. Have yourselves a good one.